Loop quantum gravity's dream is to directly quantize general relativity itself.
In 1986, Abhay Ashtekar proposed replacing the metric with an SU-2 connection.
This is the starting point of LQG. Today we discuss, after 40 years, how far has LQG come toward a theory of everything? To understand LQG, we must first understand the problem. Einstein's general relativity says gravity is spacetime curvature, described by the Einstein field equation Gov equals 8 pi GTUV.
Planck's quantum mechanics says at the Planck length Lp about 1.6 times 10 to the minus 35 meters, spacetime itself must be quantized. In 1986, Indian physicist Abhay Ashtekar proposed replacing the metric field G with an SU-2 connection A, making GR quantizable like Yang-Mills theory.
This is the starting point of loop quantum gravity. The core of LQG is quantum geometry. Classical geometry is continuous, but quantum geometry at the Planck scale is discrete, built from spin networks.
Roger Penrose proposed spin networks in 1971, edges labeled by spin quantum numbers J equals 0, 1/2, 1, 3/2, 2, nodes labeled by quantum states. The area quantization formula is A equals 8 pi gamma Lp squared times the square root of J times J plus 1, where gamma about 0.2375 is the Barbero-Emertzi parameter, determined by black hole entropy.
The volume quantization formula is V equals the sum of volume quanta at each node. This means area and volume cannot vary continuously but take discrete eigenvalues. Key techniques include Ashtekar variables and spin foams. Ashtekar proposed in 1986 replacing the metric field gauge with SU-2 connection AIA. The canonical quantization commutation relation is the commutator of A and E equals IH kappa delta function, requiring Gauss, diffeomorphism, and Hamiltonian constraints. Spin foams were proposed by Lee Smolin and Carlo Rovelli in 1993. Time evolution of spin networks forms two complexes.
The 2008 EPRL model gives 4D Lorentz invariant transition amplitudes Z equals sum over all spins J and faces F, times vertex amplitudes A and edge amplitudes B.
LQG has achieved several major successes. Thomas Thiemann proved in 1998 that the Big Bang singularity can be resolved by quantum geometry effects. Ashtekar, Pawlowski, and Singh established loop quantum cosmology in 2006, discovering the Big Bang is actually a big bounce.
Carlo Rovelli calculated black hole entropy using LQG microstates in 1996, with area eigenvalues naturally giving the correct Beacon-Stein-Hawking entropy S equals A over 4 Lp squared.
Spin foam models are naturally UV finite, requiring no renormalization. Most importantly, LQG satisfies background independence from the start. LQG's biggest challenge is unresolved dynamics.
The Hamiltonian constraint H psi equals 0, Wheeler-DeWitt equation, has no agreed-upon definition in LQG. Thomas Thiemann attempted in 1998 using the Holst action and Thiemann trick, but results depend on gauge choices. The core controversy involves Carlo Rovelli, Thomas Thiemann, Jorge Pullin, and Rodolfo Gambini proposing different quantization schemes with different results.
Currently, loop quantum cosmology is a successful simplified version, but full 3+1 dimensional LQG dynamics remains unestablished. LQG's second challenge is the semiclassical limit. The core question: how to recover classical spacetime from quantum geometry. This requires collective behavior of many spin foams producing smooth spacetime, WKB approximation satisfied, and classical Einstein equations emerging from quantum constraints. But the EPRL model's behavior at large spin limit is not fully understood. String theory has fixed backgrounds with easy semiclassical limits. LQG has background independence, making this the core difficulty. Numerical simulations of spin foams haven't fully matched classical gravity. LQG's third challenge is including standard model particles.
String theory naturally contains standard model particles as different vibration modes of strings, but LQG quantizes gravity directly without involving matter fields, requiring external introduction. No principal guides which matter fields should be included. A possible way out is that excited states of spin networks might correspond to matter particles. Lee Smolin suggests matter may emerge from microscopic degrees of freedom of quantum gravity, but no concrete model exists. Research in this direction is very preliminary. LQG's fourth challenge is experimental tests. LQG predictions include area and volume discrete, minimum area about LP squared, big bounce, speed of light may depend on energy, characteristic signals in primordial gravitational waves. Test pathways include CMB primordial gravitational wave signals, gamma-ray burst photon time delays, neutron interferometry tabletop experiments, gravitational wave observations of Planck scale effects. Currently no prediction verified, but LQG predictions may be tested earlier than string theory. Loop quantum gravity and string theory are two different approaches to quantum gravity. LQG's basic objects are spin networks and spin foams, string theories are strings. LQG is 4-dimensional, string theory needs 10 or 11 dimensions. LQG satisfies background independence, string theory doesn't. LQG doesn't need supersymmetry, string theory does. Both calculate black hole entropy, but LQG resolves singularities while string theory doesn't. Smolin argues LQG is more fundamental, Witten argues string theory is the unified theory. No conclusion yet. Loop quantum gravity may be correct, but there's a long road to a theory of everything. Reasons for optimism: singularity resolution successful, black hole entropy consistent with string theory, background independence is a fundamental advantage. Reasons for pessimism: dynamics not fully resolved, semi-classical limit difficult, matter content unclear, experimental tests far away. My judgment: LQG may be correct, but becoming a TOE still requires 30 to 50 years. Greatest hope comes from cosmological observations. Primordial gravitational waves and CMB may provide decisive evidence. LQG has profoundly changed our understanding of quantum spacetime. The exploration itself is already written into the history of science. Thank you all.